Hey everyone, welcome to this explainer. Today, we're jumping right into the deep end of the AWS DevOps lifecycle. We are going to look at exactly how to build incredibly resilient systems, lock them down securely, scale them up under massive pressure, and honestly, the most important part, how to rescue failing deployments when everything is on the line. Picture this high-stakes scenario. It's deployment day. You're rolling out code to an auto-scaling group behind an application load balancer. But out of nowhere, the app just starts timing out. Traffic is spiking, the error rates are climbing, and you've got to roll back right now. Could you rescue that failing deployment in under 5 minutes without dropping a single active customer request? Well, by the end of our time together, you are going to know exactly how to architect a system that can handle exactly that. So here's our roadmap to conquer the AWS ecosystem today. We're breaking this down into 5 core pillars. First, the CI/CD pipeline. Then, automating our foundation with infrastructure as code. Third, security and compliance. Fourth, disaster recovery strategies. And finally, engineering for scaling and performance. All right, let's hit pillar number 1, the CI/CD pipeline, building with confidence. This is all about how we safely and continuously push code from developer repos straight out to production without breaking the whole system along the way. Now, consider a real-world AWS code build snippet that is basically a masterclass in what not to do. Imagine a developer just hard-coding their AWS access keys right at the top of a buildspec.yaml file, and even worse, leaving a plain text database password just sitting right there in the environment variables. Add in direct SSH commands using an instance key, and man, if that repo ever gets compromised, your entire infrastructure is basically handed over on a silver platter. So, how do we actually fix a mess like that to align with AWS security best practices? First things first, get those AWS credentials completely out of the environment variables. You want to update the code build project IAM role with the permissions it needs instead. Next, take that database password and lock it down securely as a secure string value in the AWS Systems Manager parameter store. And finally, instead of wildly dropping SSH keys into containers, you should use the Systems Manager run command to remotely and securely execute commands on your instances. Now, when it's go time for deployment, you've got 2 main routes. In-place deployments update your instances one by one. But honestly, rollbacks there take agonizingly long. If you want that 5-minute zero-downtime rollback we talked about earlier, you absolutely need a blue/green deployment using AWS CodeDeploy. It spins up an entirely new environment, the green one. If it fails, you just instantly route traffic back to the blue environment. Boom, zero downtime. Okay, moving right along to pillar 2, infrastructure as code, automating the foundation. Now that our code is actually deploying securely, we need a rock-solid automated foundation to host it all. If you're using CloudFormation templates to deploy your infrastructure, you've probably run into this headache. You have Amazon EC2 auto-scaling groups running, but the underlying machine images, the AMIs, they get outdated fast. So how do you automatically inject a newer, more secure AMI ID into your CloudFormation template without relying on some error-prone manual update? The really elegant fix here is dynamic AMI mapping. Basically, inside your CloudFormation template, you create an AWS Lambda-backed custom resource. When the stack evaluates, this custom resource triggers the Lambda function, which then runs code to fetch the absolute latest approved AMI ID. Your launch configuration then just simply references that returned ID, so your infrastructure is effectively updating itself securely. Pretty cool, right? Of course, things will inevitably break in these automated pipelines, and you need a way to catch them instantly. Think about using a custom JSON event pattern for Amazon CloudWatch. If it targets AWS code pipeline and specifically looks for the state failed without even filtering by a specific pipeline name, that single, incredibly powerful pattern will successfully catch failed deploy and build actions across all of your infrastructure pipelines in real time. That brings us to pillar 3, security and compliance. Guarding the cloud. Look, automating infrastructure is fantastic, but automating our security guardrails is what actually keeps our companies out of the headlines. Let's throw a terrifying scenario out there. Imagine a government agency storing highly confidential files in an S3 bucket, which is strictly restricted to a specific on-prem Active Directory group. Now, an administrator makes a tiny mistake and accidentally alters the IAM policy, suddenly opening up access to the public. How do you detect and revert that massive security blunder before sensitive data leaks? Well, humans are just too slow for this. We need auto-remediation. Here's the fastest workflow to shut that down. First, configure an AWS config role designed to monitor that specific critical IAM policy. The absolute second someone makes an unauthorized modification, that config role triggers. That trigger then executes a pre-programmed AWS Lambda function that instantly reverts the policy back to its secure state. The vulnerability is quite literally closed in seconds.
Now take that same automated mindset and apply it to global compliance. If auditors suddenly ask you to prove every single Elastic Block Store volume is encrypted across all your global regions, please don't write custom scripts for that. Just deploy an AWS config manage rule using CloudFormation stack sets across all your accounts. You can consolidate the results in S3 and let Amazon SNS ping you with alerts for any violations. It's the absolute least amount of operational overhead for a massive global audit.
All right, on to Pillar 4, disaster recovery strategies, preparing for the worst. Because what happens when the cloud itself just has a really bad day? We need to make sure our systems stay online, even if an entire AWS availability zone or region fails. Before we even think about building a DR architecture, we've got to get our constraints straight. That means understanding RPO versus RTO. Recovery point objective, or RPO, is your acceptable data loss. So if your RPO is 15 minutes, you need to be backing up at least every 15 minutes. Recovery time objective, or RTO, is your acceptable downtime, basically how fast you absolutely need to be back online. Let's say you've got a flagship RDS database that normally takes a team 7 grueling hours of manual effort to recover in a different region. We can shrink that RTO to minutes. We use CloudWatch events to schedule an RDS snapshot that perfectly matches our RPO. Then, we use SNS topics to listen for those backup events, which triggers AWS Lambda functions to automatically copy that snapshot to a failover region and restore it. Literally zero manual intervention required. But wait, how do we actually get the users routed over to that disaster recovery region? That's where Amazon Route 53 failover routing steps in. If you've got an application load balancer in your primary region, Route 53 acts as the ultimate traffic cop. It's constantly monitoring health checks. The second your primary region goes dark, Route 53 seamlessly shifts every single user over to a standby application stock in your DR region. It requires the least amount of application changes, and it totally saves the day. Finally, Pillar 5, scaling and performance, engineering for growth. We've secured it, we've backed it up, now we have to handle massive data growth and traffic spikes gracefully without everything crashing down. Picture a massive online forum storing tons of thread metadata in Amazon DynamoDB. You need to run highly specific searches, stuff like finding subjects within a specific forum or a certain time frame, all while keeping your provisioned read capacity units and, more importantly, your AWS bill as low as possible. To get that kind of data set running perfectly without breaking the bank, we've got to nail the schema layout. Based on the query requirements, you'd set your partition key to subject and your sort key to forum name. But here is the real secret sauce. Create a local secondary index, an LSI, with thread as the sort key, and then use fetch operations just for the last post date time. That setup perfectly decrypts complex query requirements without chewing through expensive read capacity. Okay, one last scenario. What if you're streaming that DynamoDB data out to Lambda functions for real-time processing? Say your Lambdas are counting items, maybe checking inventory levels, but suddenly, bam, a massive traffic spike hits. The Lambda functions start failing because the DynamoDB stream is throwing throttling errors. What is the most cost-effective way to fix this massive data ingestion bottleneck? The play here? You've got to upgrade your streaming infrastructure. You swap out those DynamoDB streams and use Amazon Kinesis streams instead. Kinesis is literally purpose-built to act as a massive shock absorber for high-throughput streaming data. From there, you use Kinesis analytics to trigger your Lambda functions. It is absolutely the superior, highly scalable choice that will drastically cut down your operational overhead when things get crazy under load. Wow, we have covered a ton of ground today. Everything from fixing those terrifyingly insecure build specs and automating dynamic AMIs, all the way to auto-remediating IAM policies and orchestrating cross-region failovers. But knowledge is only power if you actually use it. So I'm going to leave you with this. If your primary AWS region went totally dark right this second, looking at the 5 pillars we just broke down, what is the weakest link in your DevOps lifecycle? Take what you learned here, go audit your infrastructure, and start building with confidence. See you next time on The Explainer.